Hi, my name is Ifan. I'm here to tell you about our paper Input Level Inductive Biases for 3D Reconstruction. Understanding 3D environment is a fundamental research question in computer vision. But so far, the research around 3D vision has been focusing on crafting specialized architectures for specific tasks of interest. This makes it very difficult to build a general perceptual system which can handle most perceptual problems. Recently, Perceiver and Perceiver.io have successfully demonstrated the concept of general-purpose networks, where a single unified architecture can complete different tasks using distinct or combined sources of inputs. These models can potentially be the key to a general perception system. However, without the built-in inductive biases from the network architecture, general-purpose models are less data efficient, meaning they are less accurate given a fixed data budget. Our goal is to use the general-purpose architecture for 3D inference tasks, but still be able to leverage 3D priors such as camera position, known correspondences, etc. Essentially, our key idea is to replace the architecture engineering with input engineering. We want to construct inputs which provide the network with useful information to derive effective inductive biases for 3D reasoning. You can think of prior work as embedded systems, where the 3D priors are hardwired into the system's architecture, whereas our goal is to have a general-purpose PC and be able to load different 3D priors like loading softwares for different tasks. In this paper, we built our experiments focusing on a well-studied and fundamental task in computer vision, depth estimation from stereo images. And we focus on two design questions. What are the most important components for 3D reasoning and how to parameterize them? Then how do we pass the parameterized geometric cues to the network? In the paper, we invested different ways to parameterize the relative 3D positions of the pixels and the epipolar constraint, as well as two distinct ways to assemble them as part of the input features. We identified better parameterization and featureization options. I invite you to check our paper for details on implementation and evaluation. Here, I want to highlight a few key points. First, you can see that any of the proposed encodings can improve the estimation by a significant amount. Using input-level inductive biases with a very general model matches and sometimes outperforms specialized state-of-the-art methods. Feeding the geometry priors as input also enables us to refine them in an inverse problem setting. Here in this example, we show that we localize the cameras given the ground truth depth maps. In summary, we proposed a way to effectively learn 3D geometry with a new type of application-agnostic architecture by embedding geometry priors as input features. This enables exciting new direction and applications such as jointly learn the 3D priors and incorporate multimodal inputs for 3D inference, including from LiDAR and non-perspective cameras. One challenge is that since the 3D prior is no longer built in, the network must learn it from scratch. This means large and diverse training data is required to avoid overfitting. This work was done during my internship at DeepMind. I want to thank the extraordinary co-authors and colleagues for the amazing experience. Now, thank you all for listening. Hope to see some of you at CVPR in person.